Place a positive point charge, Q, in space. Its electric field points radially outward in every direction. Surround the charge with a closed surface. Stretch that surface, squeeze it, or make it irregular. The sampled radial directions still cross the boundary once. The shape changes. The total outward flux does not. Flux begins with one tiny surface patch. Call its area ds. The area vector, ds vector, points along the outward normal and has magnitude ds. At this patch, the electric field makes an angle theta with the normal. Only the perpendicular component crosses the patch. Therefore, d phi equals E dot ds vector. The dot product gives E cosine theta times ds. Now divide the entire closed surface into tiny patches and add their contributions. In the limit, the sum becomes a closed surface integral. Phi equals the closed integral over s of E dot ds vector. The small circle on the integral sign reminds us that the surface is closed. To see why the shape does not matter, follow one very narrow cone of radial directions. The cone occupies a tiny solid angle, d omega. At distance r, its cross-section perpendicular to the field has area r squared d omega. An arbitrary surface may cut the cone at a tilt. Its actual patch has area ds, while its perpendicular projection is ds cosine theta. Both describe the same cross-section. So ds cosine theta equals r squared d omega. For a point charge, Coulomb's law gives E equals q over 4 pi epsilon naught r squared. Substitute this into the local flux. D phi equals E cosine theta ds. Then d phi equals q over 4 pi epsilon naught r squared times r squared d omega. Now cancel r squared. D phi equals q over 4 pi epsilon naught times d omega. Distance has disappeared. The tilt has disappeared. A deformation can change r, theta, and ds separately, but it cannot change their flux combination. This proves the shape independence. To calculate the common total, choose the surface that makes the integral easiest, a sphere of radius r centered on the charge. On this sphere, every field vector is parallel to the outward normal. Theta is 0, so cosine theta is 1. And because every point has the same radius, E has the same magnitude everywhere on the sphere. Start from phi equals the closed surface integral of E dot ds vector. On the sphere, this becomes the integral of E ds. Since E is constant over the sphere, move E outside. Phi equals E times the integral of ds. The integral of ds over the whole sphere is its area, 4 pi r squared. Therefore, phi equals E times 4 pi r squared. Solving for E gives E equals phi divided by 4 pi r squared. Coulomb's law gives another expression for the same E. Set them equal. Phi over 4 pi r squared equals q over 4 pi epsilon naught r squared. Multiply both sides by 4 pi r squared. On the right, 4 pi cancels 4 pi, and r squared cancels r squared. Only q over epsilon naught remains. Therefore, phi equals q over epsilon naught. A charge outside a closed surface contributes no net flux. Its field enters the surface, giving negative flux, and later exits, giving positive flux. These contributions cancel. That is why the law contains enclosed charge, not every charge nearby. For any closed surface, the complete law is the closed surface integral of E dot ds vector equals the enclosed charge divided by epsilon naught. Field strength falls as 1 over r squared, while spherical area grows as r squared. Gauss's law is this exact geometric balance.